Have you ever noticed how some places on Earth seem almost impossible, as if they shouldn't exist at all? In this episode of Unearthed Secrets, we explore landscapes shaped by fire, water, pressure, and time. Places that challenge what we think the planet should look like. Before we begin, please like and subscribe, and let me know in the comments where you're watching from and what time it is for you right now. The eye that stares from the desert. In the vast emptiness of the Western Sahara, far from cities, roads, and permanent rivers, there exists a structure so large that it cannot be recognized from the ground. From desert level, it appears as low rocky hills, broken plateaus, and scattered ridges blending into sand and stone. But from the air, and especially from space, a different image emerges, perfectly circular, layered, enormous. This is the Risha structure, more commonly known as the Eye of the Sahara. Measuring nearly 40 kilometers in diameter, the Risha structure is one of the most striking geological formations on Earth. Astronauts aboard the International Space Station often use it as a landmark, a visible reference point amid the otherwise uniform desert below. Its concentric rings stand out sharply against the surrounding sands, giving the unmistakable impression of a giant eye staring upward. For decades, its appearance fueled speculation. Some believed it to be the remnant of a massive impact crater. Others proposed lost civilizations, ancient cities, or unknown forces. But the true story of the Risha structure is not one of sudden catastrophe. It is a story of deep time, slow uplift, erosion, and exposure. Geology unfolding patiently over hundreds of millions of years. The rocks that make up the Risha structure are ancient. They date back to the Proterozoic and early Paleozoic eras, between 1 billion and 400 million years ago. At that time, this part of Africa lay beneath shallow seas, accumulating layers of sediment, sandstone, limestone, shale, deposited gradually over immense spans of time. These layers hardened into rock long before the Sahara existed. Much later, tectonic forces began to affect the region. Unlike areas shaped by violent plate collisions, the Risha area experienced gentle uplift. Magma intruded beneath the surface but never erupted explosively. Instead of forming a volcano, the underlying rock slowly bulged upward, creating a broad dome. This uplifted dome is the key to understanding the Risha structure. As the land rose, it exposed different rock layers to erosion. Over millions of years, wind, temperature changes, and occasional water wore away the softer layers faster than the harder ones. The result was a series of concentric rings, each representing a different geological layer with different resistance to erosion. What looks like a perfect circle from above is actually a deeply eroded geological dome, stripped down to its internal structure. The eye is not a crater formed by impact from above, but a feature revealed from within. The center of the Risha structure consists of older rock, volcanic and metamorphic material, while the outer rings are younger sedimentary layers. This inverted appearance puzzled early researchers, who initially favored impact theories, but detailed geological mapping, mineral analysis, and field studies confirmed that no shock features associated with meteor impacts exist here. There's no melted rock, no high-pressure minerals, no impact debris. Instead, the Risha is the exposed core of a collapsed uplift, a rare and visually dramatic example of differential erosion on a massive scale. From ground level, the structure is difficult to perceive. The elevation changes are subtle. The ridges rise only tens of meters above surrounding terrain. Without aerial perspective, the circular pattern disappears. This explains why the Risha went largely unnoticed until the age of flight and satellite imagery. The surrounding desert plays a crucial role in preserving the structure's visibility. The Sahara is one of the most powerful erosive environments on Earth. Extreme temperature differences between day and night fracture rock. Wind scours surfaces relentlessly. Rare rainfall events cause sudden runoff that strips loose material away. Yet despite this harsh environment, the Risha's layered pattern persists. The reason lies in the varying hardness of its rock layers. Some resist erosion stubbornly, forming ridges. Others erode quickly, forming valleys. Together, they maintain the circular pattern even as material is removed. The Risha structure is also notable for its radial and concentric faults, fractures that guide erosion and reinforce its geometry. These faults formed as the dome uplifted and later collapsed inward slightly, creating pathways for weathering and erosion. Scientifically, the Risha provides valuable insight into how large-scale geological structures evolve without dramatic surface events. It demonstrates that immense, orderly formations can arise not from catastrophe, but from persistence. The region around the Risha is extremely remote. There are no permanent settlements within the structure. Nomadic groups occasionally pass through, using the land for grazing when conditions allow. Archaeological evidence suggests human presence in the broader region thousands of years ago, when the Sahara was greener and supported lakes, rivers, and wildlife. During those wetter periods, known as African humid phases, the Risha area may have been surrounded by grasslands rather than desert. Rock engravings and tools found in Mauritania indicate human activity when the climate allowed. But as the Sahara dried, populations retreated, leaving the structure isolated once more. This isolation has contributed to the Risha's mystique. With no roads, signage, or tourist infrastructure, it remains largely untouched. Few people stand at its center knowing what surrounds them. Fewer still traverse its rings intentionally. From space, however, the Risha is unmistakable. Astronauts have described it as one of the most visually striking features on Earth. Its symmetry stands out amid the chaos of dunes and rocky plateaus. It looks artificial. It looks deliberate. But it is entirely natural. The eye analogy persists because human perception seeks familiarity. Circular forms suggest intention. Yet geology often produces order through repetition and resistance rather than design. The Risha structure also plays a subtle role in regional hydrology. Though the Sahara is dry today, ancient river channels radiate outward from the structure, indicating that water once flowed across and through it. These channels likely followed weaker rock layers and fault lines, further reinforcing the circular erosion pattern. Mineral studies reveal complex history beneath the surface. Alkaline igneous rocks, carbonatites, and breccias suggest deep magmatic activity without surface eruption. These intrusions likely contributed to uplift and fracturing, setting stage for later erosion. In this sense, the Risha is a failed volcano, though not in the explosive sense. It represents an intrusion that reshaped the land without ever breaking through it. Over time, the dome eroded, collapsed slightly, and exposed its internal anatomy. What we see today is not construction, but excavation by natural forces. The scale of the structure defies everyday experience. At nearly 40 kilometers wide, it would take hours to cross on foot. Yet its relief is so gentle that one could walk across it without realizing its shape. Only distance reveals its form. This contradiction, massive yet subtle, defines the Risha. It is a reminder that some of Earth's greatest structures are not obvious. They require perspective. They demand distance. They reveal themselves only when we step back. In recent decades, the Risha has been drawn into popular speculation. Claims linking it to Atlantis or advanced ancient civilizations circulate widely online. These ideas persist largely because the structure looks unnatural when viewed without geological context. But evidence does not support these claims. There are no ruins, no artificial materials, no organized city layout. What exists is layered rock, eroded by time, shaped by physics. The true story is no less fascinating. The Risha shows how continents breathe, rising slowly, sagging, exposing their interiors. It demonstrates how erosion does not destroy complexity, but reveals it. And it highlights how landscapes can carry immense history while remaining quiet and overlooked. Today, climate change and desert expansion continue to shape the Sahara. Winds intensify, sand migrates. The Risha's rings remain visible, but their edges soften. Over tens of millions of years, the structure itself will likely fade, its circular pattern dissolving into plateau and plain. But for now it remains one of Earth's most recognizable geological signatures. Not a scar from space, not a lost city, not an impact wound, but a window into the deep anatomy of a continent. The eye of the Sahara does not watch us. It reveals itself. It shows that the Earth does not always record its history in mountains or canyons. Sometimes it records it in symmetry, exposed not by explosion, but by time patiently stripping away everything else. In a desert defined by absence, the Risha structure stands as a presence, not towering, not dramatic, but unmistakable from afar. A reminder that the planet's greatest stories are often written so slowly that only space itself can read them. The fire that never sleeps. On Ross Island, at the edge of Antarctica's frozen continent, a mountain rises that should not exist as it does. It stands surrounded by ice shelves, glaciers, and some of the coldest air on Earth. Yet, at its summit burns a persistent lake of molten rock. This is Mount Erebus, the southernmost active volcano on the planet, and one of only a handful of volcanoes worldwide that contain a permanent lava lake. In a land defined by ice and stillness, Mount Erebus represents constant motion. Mount Erebus is not dramatic because it erupts violently or towers above all others. Its power lies in continuity. While most volcanoes erupt briefly and then fall silent for decades or centuries, Erebus has remained active for thousands of years. Its lava lake, a churning pool of molten phonolite magma, has persisted, rising and falling, cracking and resurfacing, even as blizzards sweep across its slopes and temperatures plunge far below freezing. The geological story of Mount Erebus begins more than 1 million years ago, during a period of volcanic activity associated with the West Antarctic Rift System. This rift is part of a network of fractures in Earth's crust where tectonic plates are slowly pulling apart. As the crust thinned, magma rose toward the surface, feeding a chain of volcanoes across Ross Island. Mount Erebus emerged as the dominant feature in this volcanic field. Repeated eruptions built layers of lava and ash, gradually forming a broad, steep-sided stratovolcano. Today, Erebus rises to approximately 3,794 meters above sea level, making it one of Antarctica's tallest mountains. Its slopes are coated in ice and snow, but beneath that frozen exterior lies a continuously active volcanic system. What sets Mount Erebus apart is its magma chemistry. The lava here is rich in alkaline minerals, forming a rare type known as phonolite. This magma is more viscous than basalt, but less explosive than rhyolite, allowing gases to escape relatively freely. This steady release of volcanic gases prevents pressure from building to catastrophic levels, enabling the lava lake to persist without frequent major eruptions. At the summit crater, the lava lake occupies a vent several hundred meters across. The surface of the lake is rarely calm. Crust forms briefly, then fractures as gas bubbles rise from below. Large blocks of solidified lava break free and are pulled back into the molten interior. Occasionally, strombolian explosions eject glowing fragments into the air, which fall back into the crater or scatter across the surrounding ice. These explosions are not random. They are driven by large gas bubbles, known as gas slugs, rising through the magma column. When these bubbles reach the surface, they burst violently, releasing pressure in sudden pulses. Scientists studying Erebus use these events to better understand volcanic degassing, a process critical to predicting eruptions worldwide. Despite its remoteness, Mount Erebus has been studied extensively. Early explorers in the early 20th century, including members of Ernest Shackleton's and Robert Falcon Scott's expeditions, observed steam and volcanic activity on Ross Island. Erebus was named after HMS Erebus, one of James Clark Ross's ships, during his Antarctic expedition in the 1840s. Modern scientific study began in earnest in the latter half of the 20th century, when researchers established seasonal field camps near the volcano. Today, Mount Erebus is one of the most intensively monitored volcanoes on Earth, precisely because of its unique lava lake and extreme environment. Studying Erebus is not easy. Access requires transport by aircraft or tracked vehicles across ice shelves and glaciers. Weather can change suddenly, grounding flights for days. Temperatures at the summit can fall below 40 degrees Celsius, and winds can exceed 100 kilometers per hour. Equipment must be specially designed to operate in these conditions. Yet scientists persist, because Erebus offers insights unavailable anywhere else. The lava lake acts as a window into Earth's interior. By analyzing gas emissions, including carbon dioxide, sulfur dioxide, and rare trace elements, researchers can infer conditions deep within the magma chamber. Erebus is particularly valuable because it releases unusually high levels of carbon dioxide, providing clues about how volcanic systems contribute to Earth's long-term carbon cycle. The interaction between fire and ice here is constant. Heat from the volcano melts surrounding snow and ice, creating networks of steam vents and ice caves within the crater walls. These fumarolic ice caves are warmed by volcanic gases, forming stable environments where temperatures remain near freezing even when outside air is far colder. Inside these caves, scientists have discovered microbial life surviving in darkness, heat, and chemical-rich conditions. These extremophiles feed on minerals and gases rather than sunlight, making them of particular interest to astrobiologists studying the potential for life on other planets. Mount Erebus is often cited as a terrestrial analog for volcanic systems on Mars and icy moons like Europa. The combination of volcanic heat, ice, and subsurface chemistry provides a natural laboratory for studying how life might exist in environments once thought uninhabitable. Despite continuous activity, Erebus rarely produces large-scale eruptions. Its lava lake has existed for at least several decades, possibly much longer, though exact duration is uncertain due to limited historical observation. What is known is that the lake's level rises and falls over time, sometimes draining partially before refilling from below. These fluctuations reflect changes in magma supply and gas pressure deep within the volcano. Monitoring them helps scientists understand how magma systems breathe, a process that occurs invisibly beneath many volcanoes until it culminates in eruption. The presence of Erebus also affects surrounding ice dynamics. Heat from the volcano influences local snow accumulation and ice flow patterns. Glaciers descending from Ross Island respond subtly to geothermal warmth beneath them, altering melt rates and internal structure. Nearby lies the Erebus Ice Tongue, once a long projection of glacial ice extending into the Ross Sea. Though shaped primarily by glacial flow and ocean currents, the ice tongue existed in proximity to the volcano's thermal influence, creating one of the most unusual juxtapositions on Earth, a river of ice flowing beside a mountain of fire. Mount Erebus is also a site of tragedy. In 1979, Air New Zealand Flight 91 crashed into the slopes of the volcano during a sightseeing flight, killing all 257 people on board. The accident was not caused by volcanic activity, but by navigation and weather conditions that obscured the mountain's presence. The event remains one of Antarctica's deadliest disasters and a reminder of the region's unforgiving nature. Today, Erebus stands largely unchanged. Its summit glows faintly at times, visible to those few researchers who work nearby. At night, the lava lake casts an orange light into the polar darkness, a rare source of warmth in a frozen world. The volcano does not roar continuously. Much of the time, its activity is subtle. A low rumble, a plume of gas, a slow churn beneath a crust of cooling lava. But this quiet activity is precisely what makes Erebus extraordinary. It is not a momentary spectacle, it is a process. Geologically, Mount Erebus will not last forever. Volcanic systems shift. Magma supply can change. Lava lakes can drain and vanish. The volcano may enter periods of dormancy, or it may eventually collapse or erupt more violently. But for now, it remains one of Earth's rarest phenomena, a volcano that refuses to go cold. In Antarctica, where most change happens slowly, glaciers inch forward, ice shelves fracture over decades, Erebus provides a counterpoint. It reminds us that Earth's interior remains active even beneath the thickest ice. The mountain embodies contradiction: fire surrounded by ice, motion in a land of stillness, heat in a place defined by cold. Mount Erebus does not dominate the Antarctic skyline through size alone. It dominates through persistence. It shows that the planet does not rest, even at its edges. That energy from deep within continues to reach the surface, and that some of Earth's most powerful forces operate quietly, without spectacle, year after year. The lava lake churns whether anyone is watching or not. The gases rise whether conditions are calm or severe. The mountain endures while ice flows around it. Mount Erebus is not a volcano waiting to erupt. It is a volcano that is already doing what it does best, releasing Earth's inner heat into a frozen world. And in that constant release, it stands as one of the clearest reminders that even in the coldest place on Earth, the planet is alive. The fire that would not go out. In the heart of the Karakum Desert, one of the most remote and sparsely populated regions in Central Asia, there exists a fire that has burned continuously for more than half a century. It does not flicker like a campfire or rise and fall with the seasons. It doesn't spread, and it does not move. It simply burns day and night, in the same place under the same sky, regardless of wind, temperature, or time. This is the Darvaza Gas Crater, more widely known as the Door to Hell. The crater lies in central Turkmenistan, roughly 260 kilometers north of the capital city, Ashgabat. The surrounding landscape is vast, flat, and unforgiving. The Karakum Desert covers nearly 70% of the country, composed primarily of sand dunes, gravel plains, and dry clay flats. Vegetation is scarce. Human settlements are few and far between. For most of the year, temperatures swing between extremes, with blistering heat in summer and biting cold in winter nights. In this environment, the crater stands out not only because of its fire, but because of its suddenness, a massive hole in the earth where none should exist. The Darvaza crater is approximately 70 meters wide and around 30 meters deep, though measurements vary slightly depending on erosion and internal collapse. Inside the crater, hundreds of small flames burn simultaneously, fed by natural gas seeping from underground deposits. The walls glow orange at night, and the heat can be felt from several meters away. From a distance, the crater appears like a wound in the desert floor, illuminated from within. Despite its otherworldly appearance, the origin of the crater is not ancient, nor is it the result of natural volcanic activity. It's widely believed to have formed in 1971 during a Soviet-era drilling operation. At the time, Turkmenistan was part of the Soviet Union, and the region was being surveyed for oil and natural gas reserves. The Karakum Desert sits atop one of the largest natural gas fields in the world, and Soviet engineers were actively drilling exploratory wells across the region. According to the most commonly cited account, a drilling rig operating near the village of Darvaza struck a pocket of natural gas beneath the surface. The ground beneath the rig collapsed, swallowing the equipment and forming a large sinkhole. While no casualties were reported, the sudden collapse exposed a significant quantity of methane gas. Methane is colorless, odorless, and highly flammable. It's also dangerous when released into the atmosphere in large quantities, both because of its explosive potential and its role as a greenhouse gas. Faced with a rapidly leaking gas field, Soviet engineers reportedly made a decision that would shape the site's future for decades. They ignited the gas, believing that it would burn off within a matter of days or weeks. The expectation was that once the exposed gas was consumed, the fire would extinguish itself, leaving behind a harmless crater. That expectation proved incorrect. The gas did not run out. Instead, it continued to seep from the ground, feeding the flames continuously. Days turned into weeks. Weeks turned into months. Eventually, it became clear that the underground gas supply was far larger than anticipated. The fire continued to burn, and by the time Turkmenistan gained independence in 1991, the crater had already been burning for 20 years. Today, more than 50 years later, the fire is still active. While the 1971 drilling accident is the most widely accepted explanation for the crater's formation, it is important to note that official documentation from the Soviet era is scarce. Records were often incomplete, classified, or lost, following the collapse of the Soviet Union. Some geologists have suggested alternative explanations, including natural subsurface collapse unrelated to drilling, though these theories are less commonly supported. Regardless of the precise sequence of events, the result is the same: an exposed natural gas field burning openly in the desert. The Darvaza crater is not the only gas crater in the area. Nearby, there are at least two other collapsed pits, one filled with water and another containing bubbling mud. These features suggest a broader zone of unstable subsurface geology, rich in gas deposits. However, the door to hell is by far the most dramatic and well-known of the three. At night, the crater becomes visible from kilometers away. The flames reflect off the desert sand, and the air above the pit shimmers with a heat. The sound is constant, a low, roaring hiss produced by gas combustion. Standing at the edge, visitors often describe a sense of vertigo, not just from the depth, but from the sheer scale of the fire below. For decades, the crater remained largely unknown outside the region. Turkmenistan itself was, and remains, a relatively closed country, with limited tourism and strict controls on foreign access. It was not until the early 2000s that images of the burning crater began to circulate more widely, shared by geologists, journalists, and travelers who had managed to visit the site. As photographs spread, the crater gained its ominous nickname. The Door to Hell is not an official designation, but it captured public imagination. The name reflects both the appearance of the crater and the unease it inspires. A pit of fire in the middle of an empty desert, burning without pause, evokes imagery deeply embedded in human culture and belief systems. Yet, unlike mythological or religious depictions of eternal fire, this one is entirely real and entirely man-made. Despite its dramatic reputation, the crater has never been formally developed as a tourist attraction. There are no fences, no viewing platforms, and no official safety infrastructure. Visitors typically arrive by four-wheel drive vehicles, often guided by locals who know the desert routes. The nearest village is small, and basic accommodations are limited. Most visitors camp overnight, drawn by the opportunity to see the crater after dark. The lack of development is partly due to Turkmenistan's approach to tourism, but also to safety concerns. The ground around the crater is unstable, and smaller collapses have been observed over time. The heat is intense, and toxic gases may be present in low concentrations near the rim. There is no official monitoring system for structural integrity or air quality at the site. From a scientific perspective, the crater presents both challenges and opportunities. On one hand, it represents a continuous release of methane, a potent greenhouse gas, while much of the methane is burned off through combustion, reducing its immediate climate impact. The site still represents a loss of natural resources and an ongoing environmental issue. On the other hand, the crater provides a rare, long-term example of uncontrolled gas combustion in a natural setting, offering insights into subsurface gas dynamics and combustion behavior. In recent years, the Turkmen government has expressed interest in extinguishing the fire. In 2010, then-President Gurbanguly Berdimuhamedow publicly ordered scientists to find a way to close the crater, citing environmental concerns and the loss of valuable natural gas. Similar statements were made again in 2022, when the government renewed efforts to address methane emissions across the country. Despite these declarations, the fire continues to burn. Extinguishing the crater is not a simple task. The precise structure of the gas field beneath the crater is not fully mapped, and sealing it could require extensive drilling, pressure control, and risk assessment. Improper intervention could potentially lead to further collapses or uncontrolled gas release elsewhere in the area. There's also the question of cost and benefit. The amount of gas lost through the crater, while significant, represents only a fraction of Turkmenistan's total reserves. The technical challenge and expense of extinguishing the fire may outweigh the perceived benefits, particularly in a remote region with little infrastructure. Meanwhile, the crater has become an unintended symbol of the country. Images of the door to hell appear in documentaries, travel features, and scientific discussions around the world. It is often cited as an example of industrial hubris, a reminder of how short-term decisions can produce long-lasting consequences. Yet it is also a testament to the sheer scale of natural gas reserves beneath the Earth's surface and the difficulty of controlling them once exposed. For the people who live in the surrounding region, the crater is neither myth nor metaphor. It's simply part of the landscape. Local shepherds have grazed livestock nearby for decades, keeping a respectful distance from the pit. Some residents recall when the fire first appeared, though first-hand accounts are becoming rarer as time passes. For younger generations, the crater has always been there, a constant presence in an otherwise shifting world. At sunrise, the flames appear less dramatic, muted by daylight. Heat still rises from the pit, and the gas continues to burn, but the crater blends more easily into the desert. It is at night that the site reveals its full impact, when darkness amplifies the glow and the fire dominates the horizon. There is no official estimate for how long the crater will continue to burn. Some experts suggest it could last decades more if the gas supply remains steady. Others believe the flow may eventually diminish as pressure decreases or underground pathways shift. Until then, the fire persists, sustained by forces far below the surface. The Darvaza Gas Crater is not a relic of ancient civilization, nor is it a natural wonder shaped over millennia. It is a modern phenomenon, born of industrial exploration and human decision-making. Its continued existence raises questions about responsibility, environmental management, and the long-term consequences of energy extraction. In the silence of the Karakum Desert, the fire continues to burn, indifferent to borders, politics, or time. It does not announce an ending, nor does it offer resolution. It simply remains, an open flame in the earth, a reminder that some actions, once set in motion, are not easily undone. And so the door to hell stays open, not because of legend or prophecy, but because the ground beneath it still breathes fire. The sea that disappears. Along the eastern coastline of India, where the Bay of Bengal meets long stretches of sand and scrub, there exists a shoreline that behaves in a way few coastlines on Earth do. Twice each day, the sea arrives as expected. Waves rolling in, foam breaking along the shore, water stretching to the horizon, and then slowly and almost deliberately, it leaves. Not by retreating a few meters, as tides usually do, but by withdrawing for kilometers, what remains is not a beach, but an exposed seabed, flat, rippled, and strangely quiet. This place is Chandipur, and the phenomenon is known as the vanishing sea. Chandipur is located in the Indian state of Odisha, approximately 16 kilometers from the city of Balasore. It is a small coastal settlement, modest in scale, bordered by casuarina trees, sandy dunes, and tidal flats. On maps, it appears unremarkable, just another point along India's vast eastern coastline. Yet what occurs here has puzzled visitors, inspired local traditions, and drawn scientific attention for decades. The defining feature of Chandipur is its extreme tidal retreat. During low tide, the sea can recede as far as 5 kilometers from the shoreline. Where waves once stood, only wet sand, shallow channels, and scattered marine life remain. The ocean doesn't vanish instantly. It withdraws gradually, almost patiently, exposing layer after layer of seabed. For hours, the coastline transforms into a wide, open plain, stretching far beyond where the eye expects water to be. Unlike dramatic natural disasters or sudden geological events, Chandipur's transformation is quiet. There's no violent motion, no crashing sound to mark the change. The sea simply moves away, leaving behind a space that feels temporary, as though borrowed from the ocean rather than claimed from it. The phenomenon occurs twice daily, following the rhythm of tides, but its scale is what makes Chandipur exceptional. While tidal changes are common across the world, the degree of retreat here is rare. In most coastal regions, low tide exposes a narrow strip of beach. In Chandipur, the exposure is vast enough for people to walk kilometers into what was once open sea. For generations, local residents have lived alongside this rhythm. Fishing practices have adapted to it. Children grow up watching the water come and go, learning instinctively when the sea is safe and when it will return. To outsiders, the vanishing sea feels uncanny, even unsettling. To locals, it is simply how the coast breathes. Scientifically, the explanation for Chandipur's disappearing sea lies in a combination of factors rather than a single cause. The Bay of Bengal experiences strong tidal forces, influenced by the gravitational pull of the moon and the shape of the continental shelf. In this region, the seabed slopes very gradually, creating a shallow coastal gradient. When the tide retreats, even a small vertical drop in sea level translates into a large horizontal movement of water. This gentle slope is key. The seabed near Chandipur extends outward with minimal depth change for several kilometers. As the tide ebbs, the water pulls back across this flat expanse, exposing the seabed far more dramatically than in areas where the seafloor drops off quickly. Additionally, the coastline here is shaped by sediment deposits carried by rivers flowing into the Bay of Bengal. Over thousands of years, silt, sand, and clay have accumulated, creating broad tidal flats. These sediments are compacted and reshaped continuously by tidal motion, reinforcing the flatness of the seabed. Wind patterns also play a role. Seasonal winds can influence surface water movement, subtly enhancing the retreat during certain times of the year. Together, these elements create the conditions necessary for the sea's dramatic withdrawal. Despite these explanations, Chandipur still resists complete predictability. The exact distance the sea retreats varies depending on lunar cycles, seasonal changes, and weather conditions. Some days, the exposed seabed stretches farther than usual. On others, the retreat is less pronounced. This variability adds to the sense that the sea here follows its own rules. Walking on the exposed seabed reveals a landscape rarely seen. The surface is marked by ripples shaped by flowing water, shallow channels where small streams drain back toward the ocean, and patches of soft sand interspersed with firmer ground. Tiny crabs scuttle across the surface, retreating into burrows as footsteps approach. Shells, small fish, and marine plants are scattered across the flats, temporarily stranded until the water returns. The experience can feel disorienting. With no visible waves and no immediate horizon of water, it is easy to forget that the sea is merely absent, not gone. The air smells faintly of salt and damp earth. The ground beneath foot feels alive, subtly shifting under pressure. Yet this exposed world is temporary. The tide will return, and when it does not announce itself dramatically. The water creeps back slowly at first, filling channels and depressions, then advancing steadily across the flats. Those who linger too long can find themselves surrounded by shallow water, forced to retreat as the sea reclaims its space. This rhythm has shaped local customs and cautionary knowledge. Residents understand the timing of the tides intuitively. Visitors are often warned not to wander too far without awareness of the sea's return. There are no barriers or fences marking how far one can walk. The boundary exists only in time. Historically, Chandipur's coastline has been known and inhabited for centuries. Odisha's coast has long played a role in regional trade, fishing, and cultural exchange. While Chandipur itself was not a major port, it existed within a broader coastal ecosystem shaped by maritime activity. The vanishing sea likely influenced settlement patterns, fishing schedules, and local beliefs, long before it attracted scientific attention. Local folklore offers its own interpretations. Some stories speak of the sea bowing in respect to unseen forces. Others describe the retreat as a form of breathing, a living rhythm shared between land and water. These narratives don't seek to explain the phenomenon scientifically, but instead integrate it into a worldview where natural processes carry meaning beyond mechanics. In modern times, Chandipur gained wider recognition during the 20th century, particularly after India's independence. As coastal tourism developed, Chandipur became known as a place where the sea disappears. Visitors arrived out of curiosity, drawn by photographs and word-of-mouth accounts. The area was eventually developed modestly, with small hotels, guest houses, and access roads. Despite this, Chandipur has never become a heavily commercialized tourist destination. Its appeal lies in simplicity rather than spectacle. There are no towering resorts or crowded promenades. The experience remains closely tied to observation and timing, being present when the sea withdraws, and again when it returns. Beyond tourism, the region surrounding Chandipur holds strategic significance. Nearby Balasore district is home to defense and research facilities, including missile testing ranges operated by India's defense organizations. These installations are separate from Chandipur itself, but their presence has influenced regional development and access. Certain coastal areas are restricted, adding an additional layer of controlled space along the shoreline. This proximity to high-security zones has sometimes fueled speculation and rumors. Some visitors have imagined hidden connections between the vanishing sea and secret installations. There's no evidence to support such claims. The tidal phenomenon at Chandipur is entirely natural, shaped by geography and ocean dynamics rather than human intervention. From an environmental perspective, Chandipur's tidal flats form a fragile ecosystem. The exposed seabed supports microorganisms, small crustaceans, and marine plants adapted to alternating periods of submersion and exposure. These organisms play a role in nutrient cycling and provide food for fish and birds. Disturbance of the flats, through pollution, construction, or excessive foot traffic, could disrupt this balance. Climate change adds further uncertainty. Rising sea levels, altered tidal patterns, and increased storm activity in the Bay of Bengal may affect Chandipur's coastline in the future. It is unclear how these changes will influence the vanishing sea. The gradual slope of the seabed may amplify certain effects, potentially altering the extent or timing of tidal retreat. Researchers continue to study coastal dynamics in the region, though Chandipur itself remains less extensively monitored than major ports or its erosion hotspots. Its relative isolation and modest development have preserved much of its natural character, but they have also limited comprehensive long-term data collection. For those who visit, the most striking aspect of Chandipur is not simply the absence of water, but the sense of time it creates. The landscape feels borrowed, existing only for a few hours before being erased. Footprints left on the seabed are temporary. Paths vanish. The boundary between land and sea becomes fluid, uncertain. At sunrise, when the tide is low, the exposed flats glow softly, reflecting the sky's changing colors. By afternoon, the same area may be submerged once again, waves moving over ground that was walked upon earlier that day. This constant transformation challenges the assumption that coastlines are fixed. Unlike cliffs carved over millennia or monuments built to endure, Chandipur offers no permanence. Its defining feature is repetition without stability, a cycle that never settles into a final form. The sea does not retreat permanently, nor does it remain. It comes and goes, indifferent to observation. For local communities, this rhythm continues to shape daily life. Fishing schedules align with tidal cycles. Children learn where not to wander. Elders pass down knowledge of the sea's behavior not through charts, but through experience. The phenomenon is not extraordinary to them. It is practical, familiar, and quietly respected. Chandipur does not roar like a storm or erupt like a volcano. It does not dominate the skyline or announce itself with sound. Its mystery lies in subtlety, in the slow, deliberate withdrawal of something expected to stay. The sea, usually constant and defining, chooses absence here, if only temporarily. There is no gate, no marker, no moment where the vanishing is complete. The process is gradual enough that one can watch it happen, step by step, wave by wave. And when the water returns, it does so without ceremony, reclaiming the land as if it had never left. In a world where natural wonders are often defined by excess, height, depth, violence, scale, Chandipur stands apart. Its power lies in restraint. The sea simply steps away, leaving silence in its place, and then, as always, it comes back. The white cascades of stone. In southwestern Turkey, rising above the plains of the Menderes River Valley, there's a hillside that appears unreal at first glance. From a distance, it looks like snow draped across a mountain, frozen in motion. As one draws closer, the illusion deepens. The surface gleams white under the sun, shaped into terraces, basins, and flowing contours that resemble waterfalls paused in time. This is Pamukkale, a natural formation created not by ice or salt, but by water, heat, and stone. Pamukkale, which translates from Turkish as Cotton Castle, is located near the city of Denizli. For thousands of years, people have been drawn to this site, not only for its striking appearance, but for the warm, mineral-rich waters that continue to flow across its slopes. These waters have shaped the terraces slowly and continuously, turning liquid into rock and movement into permanence. The travertine terraces of Pamukkale are formed by calcium carbonate deposits left behind by thermal spring water. Beneath the surface of the region lies a complex network of geothermal activity. Rainwater seeps deep into the earth, where it is heated by geothermal energy and enriched with dissolved minerals, particularly calcium bicarbonate. When this hot water rises back to the surface through faults in the Earth's crust, it cools and releases carbon dioxide. As the gas escapes, calcium carbonate precipitates out of the water, settling as a white solid. Over time, this process builds layer upon layer of travertine, a form of limestone. The terraces form naturally as water flows downhill, spilling over edges and depositing mineral residue along the way. Small variations in slope, water speed, and mineral concentration create the stepped pools that define Pamukkale's appearance. This is not a fast process. Each terrace forms over decades and centuries, shaped by countless flows of water. The result is a landscape that feels sculpted yet alive, constantly changing even as it appears frozen. The water that feeds Pamukkale emerges at temperatures between 35 and 100 degrees Celsius, depending on the spring. As it spreads across the terraces, it cools rapidly, becoming suitable for bathing within minutes of surfacing. This combination of warmth, mineral content, and visual beauty has made the site attractive to humans since antiquity. Long before Pamukkale became a symbol of Turkey's natural heritage, it was part of an ancient city. In the 2nd century BCE, the Hellenistic city of Hierapolis was founded atop the terraces by the Attalid dynasty of Pergamon. The city was later absorbed into the Roman Empire, where it flourished as a center of health, religion, and leisure. To the Romans, the thermal waters of Pamukkale were not merely a curiosity. They were believed to possess healing properties. Bathing complexes were constructed around the springs, and people traveled long distances to soak in the mineral-rich pools. The water was thought to ease joint pain, skin conditions, and internal ailments, though these beliefs were based more on tradition than controlled medical study. Hierapolis grew into a significant urban center, complete with temples, theaters, necropolises, and public baths. The city was built directly atop the travertine formations, integrating natural and constructed spaces. Columns rose beside flowing mineral water. Stone streets led to pools fed by geothermal springs. Earthquakes were frequent in the region, and Hierapolis suffered repeated destruction and rebuilding. Each collapse left layers of rubble that mingled with travertine deposits, creating a complex archaeological record. Despite this instability, the city endured for centuries, sustained by the very geological forces that threatened it. By the Byzantine period, Hierapolis began to decline. Shifts in trade routes, political instability, and ongoing seismic activity gradually reduced its population. Eventually, the city was abandoned. What remained were ruins embedded in a white mineral landscape, slowly reclaimed by natural processes. For centuries after, Pamukkale remained relatively isolated. Local populations were familiar with the site, but it was not widely known beyond the region. Travelers passing through described a white mountain that shimmered in the sun, but detailed scientific understanding came much later. In the modern era, Pamukkale's striking appearance began to attract attention from researchers, photographers, and tourists. By the mid-20th century, it had become a popular destination, both for its natural beauty and for the ruins of Hierapolis. However, this popularity came at a cost. As tourism increased, hotels were built directly on top of the travertine terraces. Thermal water was diverted into swimming pools, and visitors walked freely across the formations, wearing shoes that eroded the fragile surfaces. Vehicles were driven near the pools. The natural flow of water was disrupted, causing some terraces to dry out and to turn gray. Travertine is durable over geological timescales, but fragile in the face of sudden change. Without continuous water flow, the white calcium carbonate darkens and cracks. By the 1980s, visible damage had accumulated across large sections of Pamukkale. Recognizing the threat, Turkish authorities began taking action. In 1988, Pamukkale and Hierapolis were designated a UNESCO World Heritage Site. This status brought international attention and pressure to preserve the landscape. Hotels were demolished, roads were removed, and water flow was carefully managed. Strict regulations were introduced. Visitors were required to remove their shoes before walking on the terraces to reduce abrasion. Access was limited to specific areas. Water was redirected to ensure even distribution across the formations, allowing damaged sections to recover gradually. These measures were not without controversy. Some local businesses were affected by the restrictions and balancing. Conservation with the tourism proved challenging. However, over time, the terraces began to regain their whiteness, demonstrating the resilience of the formation when given appropriate conditions. Today, Pamukkale is both a natural phenomenon and a carefully managed site. The terraces remain active, shaped daily by flowing water. Some pools are filled and drained in rotation to prevent overuse. Others are closed entirely to allow regeneration. Visitors now approach the site on foot, ascending the hillside barefoot, following designated paths. The experience is tactile as well as visual. The warm water flowing around ankles, the textured stone beneath foot, the contrast between smooth basins and rough edges. The water itself remains a central attraction. In addition to the terraces, visitors can swim in the so-called Cleopatra's Pool, a thermal basin filled with submerged Roman columns. This pool is fed by the same geothermal system and maintains a steady temperature year-round. While the historical connection to Cleopatra is likely a later invention, the pool does sit within the ruins of Hierapolis and offers a rare opportunity to bathe among ancient stone. Scientifically, Pamukkale continues to be a site of interest. Researchers study the rate of travertine deposition, the chemistry of the water, and the interaction between microbial life and mineral formation. Certain microorganisms play a role in trapping calcium carbonate, subtly influencing the texture and growth of the terraces. The site also serves as a case study in conservation. Pamukkale demonstrates how human intervention can both damage and restore natural systems. Without regulation, the terraces degraded rapidly. With careful management, they began to recover, though they will never return entirely to a pre-modern state. Climate change introduces new uncertainties. Changes in rainfall patterns, groundwater levels, and temperature could affect the geothermal system that feeds Pamukkale. Reduced water flow could slow travertine formation, while increased tourism pressure could strain management efforts. Long-term preservation will depend on continued monitoring and adaptation. Despite these challenges, Pamukkale remains one of the most visually distinctive landscapes on Earth. Unlike mountains shaped by tectonic uplift or canyons carved by rivers, it is built layer by water, leaving something behind. Each drop contributes to the whole. At sunrise, the terraces reflect soft light, their surfaces glowing pale gold and white. At midday, they appear almost blinding under direct sun. At sunset, shadows settle into the basins, emphasizing depth and contour. At night, when the site is quiet, the sound of water continues, flowing as it has for millennia. What makes Pamukkale enduring is not just its beauty, but its process. It is a reminder that landscapes are not static. They are systems in motion, shaped by chemistry, gravity, and time. Stone forms not only through pressure and force, but through patience. For ancient visitors, Pamukkale was a place of healing. For modern visitors, it is a place of wonder. For scientists, it is a living laboratory. And for the land itself, it is simply a moment in a much longer transformation. The terraces will continue to grow as long as water flows and minerals precipitate. Edges will thicken, pools will shift. Some surfaces will erode while others form anew. The cotton castle will change, slowly and quietly, one layer at a time. In the hills above Denizli, water emerges from the earth carrying dissolved stone. As it flows, it leaves its burden behind. What remains is a white cascade, shaped by repetition, held in balance between motion and stillness. Pamukkale does not erupt, collapse, or vanish. It accumulates, and in doing so, it records the passage of time not in years, but in layers of stone laid down by flowing water that never stops. The geyser that was never meant to exist. In the high desert of northwestern Nevada, far from national parks, tourist centers, or marked scenic routes, there's a structure that looks more like a science fiction artifact than a natural landform. It rises from flat desert ground in layers of red, green, and yellow stone, steaming quietly into the open air. Water spills from its crown continuously, never erupting, never stopping. This is Fly Geyser, a geothermal formation created not by nature alone, but by accident, persistence, and time. Fly Geyser is located on private land near Fly Ranch, close to the small town of Gerlach, Nevada, at the edge of the Black Rock Desert. The surrounding environment is stark and expansive. The land is dry, windswept, and sparsely vegetated, defined by alkaline flats and distant mountain ranges. Summer temperatures can be extreme, winters cold and isolating. In this setting, the geyser stands out immediately, not for its size, but for its color, motion, and origin. Unlike famous geysers such as Old Faithful and Yellowstone National Park, Fly Geyser is not the result of long-term natural geothermal venting shaped solely by geological forces. It exists because of human error layered onto natural heat beneath the Earth's crust. The story of Fly Geyser begins in 1916, when settlers drilled a well in the area searching for water suitable for agriculture. At the time, geothermal activity in the region was known, but poorly understood. When the well was drilled, it struck a source of geothermally heated water. The water that emerged was extremely hot and heavily mineralized, unsuitable for irrigation. The well was capped and the site was abandoned. For decades, the land remained quiet. Then, in 1964, a geothermal energy company returned to the area and drilled a second well nearby, this time exploring the potential for energy production. The drilling penetrated a pressurized geothermal reservoir. Once again, hot water surged upward, but this time, the well was not sealed properly. The result was a continuous release of superheated water rich in dissolved minerals. With nowhere else to go, the water began flowing out of the ground and into the open air. Unlike a geyser that erupts intermittently due to pressure buildup, Fly Geyser flows constantly, driven by underground pressure that never fully equalizes. At first, the structure was small. Water pooled around the opening, depositing minerals as it cooled. Over time, calcium carbonate and silica precipitated out of the water, hardening into stone. Layer by layer, the mound grew upward and outward, shaped entirely by the steady overflow. Today, Fly Geyser stands approximately 3.5 to 4 meters tall, though its exact height changes gradually as new mineral deposits accumulate and older layers erode. The mound is irregular, composed of bulbous terraces and cone-like protrusions. At its top, multiple vents release water and steam continuously. What makes Fly Geyser visually striking is not just its form, but its color. The reds, greens, oranges, and yellows that coat the surface are not paint or chemical staining. They are the result of thermophilic algae and bacteria, microorganisms that thrive in extreme heat. These organisms colonize the wet mineral surfaces, their pigments interacting with mineral deposits to create vivid coloration. Different temperatures support different microbial communities. Where the water is hottest, certain organisms dominate, producing red and orange hues. As the water cools slightly while flowing down the mound, other species take hold, adding green and yellow tones. The result is a living surface, constantly changing as water temperature, mineral content, and sunlight vary. Despite its appearance, Fly Geyser is not a true geyser in the geological sense. A true geyser requires a specific underground plumbing system that allows pressure to build until water erupts violently and intermittently. Fly Geyser lacks this mechanism. Its flow is steady, not explosive. It does not pause, and it does not surge. It simply releases water continuously, driven by underground pressure created by the improperly sealed well. For many years, Fly Geyser remained largely unknown outside the local area. It sat on private ranch land, inaccessible to the public, slowly growing without attention. There were no signs, no official recognition, and no scientific monitoring beyond occasional curiosity from geologists aware of geothermal features in the region. This obscurity began to change in the early 2000s as photographs of the geyser circulated online. Its unusual appearance attracted attention, and it quickly became known as one of the strangest man-made natural features in the United States. Despite this growing interest, access remained restricted. Unauthorized visitors sometimes attempted to reach the site, raising concerns about safety and environmental damage. In 2016, Fly Ranch was purchased by the Burning Man Project, the nonprofit organization behind the annual Burning Man event. The acquisition included Fly Geyser and the surrounding land. The organization expressed an interest in preserving the site and managing access responsibly. Since then, Fly Geyser has remained closed to general public access, with limited guided visits conducted under strict conditions. This controlled approach reflects the fragility of the formation. The mineral layers are delicate. Foot traffic can damage microbial mats that take years to establish. Changes in water flow or pressure could alter the structure permanently. From a scientific standpoint, Fly Geyser represents a rare opportunity to observe rapid geological formation on a human timescale. Unlike most landforms, which take thousands or millions of years to develop, Fly Geyser has grown noticeably within decades. Its continued growth allows researchers to study mineral deposition, microbial ecosystems, and geothermal chemistry in real time. The water emerging from Fly Geyser is extremely hot, often exceeding 90 degrees Celsius near the vent. It carries high concentrations of dissolved minerals drawn from deep underground. As the water cools upon reaching the surface, these minerals crystallize, forming new layers of stone. Each layer records a moment in the geyser's ongoing history. The site also raises questions about responsibility and unintended consequences. Fly Geyser exists because a well was drilled without sufficient understanding of the geothermal system beneath it, and because it was not sealed properly. What began as an industrial mistake became a geological feature that now requires careful stewardship. Attempts to shut down Fly Geyser have been considered but largely rejected. Sealing the well could disrupt underground pressure in unpredictable ways. There's also concern that intervention could trigger new vents or destabilize the existing structure. For now, the decision has been to let the geyser continue flowing under controlled observation. Environmentally, the geyser has created a localized wetland in an otherwise arid landscape. Pools of warm water support insects, birds, and plant life not typically found in the surrounding desert. This microecosystem depends entirely on the geyser's continuous flow. Any change to that flow would alter the balance instantly. At the same time, the site illustrates the fine line between natural and artificial. Fly Geyser is not entirely natural, nor entirely engineered. It is a hybrid, born of human activity, shaped by geological forces, and sustained by processes beyond direct control. Visually, Fly Geyser defies expectation. It does not resemble the iconic geysers seen in national parks. There's no predictable eruption, no plume rising dramatically against the sky. Instead, there is constant motion. Water spilling, steam rising, minerals accumulating, colors shifting slowly with time. In winter, steam from the geyser rises into cold air, forming a visible column that contrasts sharply with snow-dusted ground. In summer, the colors appear more saturated under intense sunlight. At night, the structure is silent except for the sound of flowing water, glowing faintly under moonlight. There are no myths associated with Fly Geyser, no ancient stories, no cultural traditions built around it. It is too new for legend. Its story belongs entirely to the modern era, a reminder that even small decisions can create lasting changes in the landscape. Fly Geyser continues to grow. Each day, minerals are deposited, microorganisms spread and retreat. The mound shifts subtly, reshaped by gravity and flow. There's no final form toward which it is moving. Its shape tomorrow will differ slightly from its shape today. In a desert defined by dryness and distance, Fly Geyser introduces warmth, moisture, and color. It stands as evidence that the Earth's interior remains active even beneath seemingly inert land, and that when that activity is exposed, intentionally or not, it can produce something unexpected. Fly Geyser was never planned. It was never designed. It was never meant to exist, and yet it does, continuing to pour hot water into the open air, building stone from liquid, and quietly reminding us that the ground beneath our feet is not as stable or as predictable as it appears. As this journey comes to an end, these places remain, silent, powerful, and largely unchanged by our presence. They remind us that beneath the surface of the familiar world, immense forces are still at work, shaping land, fire, water, and stone over spans of time we can barely comprehend. Long after we look away, these landscapes will continue to burn, flow, rise, and shift, following rules written deep within the earth itself. Thank you for watching Unearthed Secrets. Until next time, keep looking closer at the world beneath your feet.